Hi everyone, in this video we will take Rolle's theorem, and you have to know what are the conditions of Rolle's theorem. The first condition, f must be continuous on the closed interval a and b. F must be differentiable in open interval a and b. fa equals 0 and fb equal to 0, and in more general case fa equals to fb. The conclusion, then there is C in an open interval AB such that f prime of C equal to 0. So in part A we have f of x equals 1 over 2x minus square root of x, and we have the closed interval 0 to 4. So firstly you have to verify the conditions of Rolle's theorem, and the first condition is f must be continuous in the closed interval. So you have to find the domain of your function. The domain of f is x greater than or equal to 0, because we have square root of x, so x must be greater than or equal to 0. So in our interval 0 and 4, f is continuous on the closed interval 0 and 4. Now for the second condition, you have to check if f is differentiable on the open interval a and b. So you have to find the first derivative of this function. So in part B you have to start finding f prime of x, and f prime of x equals to 1 over 2 minus 1 over 2 square root of x. So what is the domain of the function f prime? The domain is x must be greater than 0, because the square root and denominator. So domain of f prime is x greater than 0, which means that f is differentiable on the open interval 0 and 4. So the conclusion that f is differentiable on the closed and open interval 0 and 4. So the second condition satisfied. In part C you have to check if f of a equals f of b. So you have to replace the endpoints of the interval to check this condition. So in part C you have to find f of 0 and f of 4, and f of 0 equals 1 over 2 multiplied by 0 minus square root of 0, and this equals to 0. F of 4 equals 1 over 2 multiplied by 4 minus square root of 4, and this is equal to 0 also. So f of 0 equals f4 equals to 0. So all conditions of Rolle's theorem satisfied for this example. So what's the conclusion? The conclusion is then there exists C in the open interval 0, 4 such that f prime of C equal to 0. So f prime of C is 1 over 2 minus 1 over 2 square root of C equal to 0. Move this term to the right hand side, you will get 1 over 2 square root of C equals 1 over 2, and by cross multiply you will get 2 square root of C equals to 2. Divide by 2 both sides, radical C equals to 1, square for both sides, you will get C equals to 1. This is the value of C that satisfied Rolle's theorem, and that means that f prime of 1 equal to 0, and 1 in the open interval 0 and 4. For the second part, in part B, we have another function, and the function f of x equals to ln 4 plus 2x minus x squared, and we have the interval -1 to 3. So you have to check the conditions. Firstly, you have to find the domain of this function, and as you know, if we have ln function, the inside function must be greater than 0. So we have 4 plus 2x minus x squared is greater than 0. Now you have to find the zeros of this quadratic equation, and the zeros are x1 equals to 1 minus square root of 5, and x2 equals 1 plus square root of 5, and 1 minus square root of 5 equals approximately -1.23, and 1 plus radical 5 equals to 3.236. Now you have to check the sign of the function 4 plus 2x minus x squared. So we have two roots. The first one minus 1.23, and the second one 3.236. And since we have a quadratic equation, so the region between the roots will be the same as sign with the coefficient of x squared, and the coefficient of x squared is equals to -1. So this region will be positive, and this region will be negative, and this one also will be negative. Now our interval is from -1 to 3. So we are working in this area, -1 to 3. And this area, the function inside the logarithmic function is positive. So f is continuous on the open interval, on the closed interval, sorry, from -1 to 3. So the first condition satisfied for Rolle's theorem. Now the second condition, you have to check if f is differentiable or not on the interval we have. So part B, you have to find f prime firstly. F prime of x equals, since we have ln, so you have to find the first derivative of the inside function, which is 2 minus 2x divided by the inside function 4 plus 2x minus x squared. Now you have to find the domain of this function. Since we have rational function and we have polynomial in denominator, so the polynomial must be not equal to 0, and the roots of this polynomial is given in part A. We have 1 minus radical 5 and 1 plus radical 5, and since these two roots not included in the open interval from -1 to 3, then f is differentiable on the open interval from -1 to 3. Now you have to go to the third condition. You have to check that if f of a equals f of b. So you have to substitute the endpoint in the given function. So for part C, you have to check f of -1, and this is equals to ln 4 minus 2 minus 1. Give us ln of 1, and this is equal to 0. And you have to check f of 3, and you have ln of 4 plus 6 minus 9, and this is equals to ln of 1, which is also equal to 0. So what is the conclusion here? The conclusion is f of negative 1 equals f of 3. So also the third condition satisfied for Brell's theorem. Now you have to find C. Then there exists C and the open interval from negative 1 to 3 such that f prime of C equal to 0. So we can find such number that f prime of C equal to 0. And f prime of C is given here. So we have 2 minus 2c divided by 4 plus 2c minus c squared equal to 0. If we have a rational number equal to 0, then numerator equal to 0. So we have 2 minus 2c equal to 0. By solving this linear equation, you will get c equals to 1. And 1 belongs to the open interval from negative 1 to 3. And that's it. Thank you. In the second example, we have the mean value theorem, and we have two conditions for the mean value theorem. The first condition is f is continuous on the open interval, the closed interval a and b. F is differentiable on open interval a and b. And the conclusion, then there is c such that f prime of c equals f of b minus f of a divided by b minus a, which is the slope of the secant from a to b. So firstly, we have to check or verify the conditions of mean value theorem for these two parts. For part A, we have the function square root of 25 minus x squared and the closed interval minus 5 and 3. So the first condition, you have to check that f is continuous on closed interval negative 5 to 3. So you have to find the domain of this function. And as you know, the domain of square root function is the function inside must be greater than or equal to 0. So we have 25 minus x squared must be greater than or equal to 0, which is positive, and the interval from negative 5 to 3. You have to check. So what are the roots of 25 minus x squared? The roots are x equals to 5 and x equals to negative 5. After that, you have to check the sign of this function. On the number line, we have minus 5 and 5. We have the roots. Between the roots, we have different sign from the coefficient of x squared. So it will be positive, and out of roots will be negative. So our interval is from negative 5 to 3. And in this interval, the function 25 minus x squared is positive. So f continuous on negative 5 to 3. Now the second condition for the mean value theorem, you have to check that f is differentiable on the open interval minus 5 to 3. So you have to find f prime of x, and f prime of x for square root is the first derivative of the inside function, negative 2x, divided by 2 multiplied by the same square root function, 25 minus x squared. By simplifying, you will get f prime equals to negative x over square root of 25 minus x squared. Now this is f prime, and f prime is defined when denominator not equal to 0 if we have polynomial, but here we have square root and denominator, so the inside function must be greater than 0. And in the open interval from -5 to 3, this function is positive. So f is differentiable on the open interval from -5 to 3. So we verify the two conditions for the mean value theorem, and the conclusion is there exists C in the open interval from -5 to 3 such that f prime of C equals f of b minus f of a over b minus a. This is a and this is b. These are the end points of the interval. So we have f of b 3 minus f of a minus 5 divided by b minus a 3 minus -5. Now you have to replace 3 and -5 in the function f, and you will get square root of 25 minus 3 squared, which is 25 minus 9, give us 16, minus square root of 25 minus -5 squared is 0, divided by 3 minus -5, 8. So we have 4 over 8, which is half. So there exists C such that f prime of C equals to 1 over 2. Now you have to find this C, so you have to replace C in the derivative, and you will get negative C divided by square root of 25 minus C squared equals 1 over 2. By cross multiplication, you will get square root of 25 minus C squared equals minus 2C. Take power 2 to both sides. You will get 25 minus C squared equals to 4C squared. And moving negative C squared to the right hand side, you will get 5C squared equals to 25, divide 5 both sides, C squared equals to 5, take square root for both sides, C equals to radical 5, or C equals to negative radical 5. And radical 5 approximately equals to 2.24. And 2.24 is the interval from -5 to 3. This belongs to open interval from -5 to 3. And minus square root of 5 is minus 2.2, which is also belongs to our interval from -5 to 3. So we have two C's in this example. This is the first C that satisfied the mean value theorem, and this is the second one also satisfied the mean value theorem. Now in part B we have another function, f of x equals 1 minus 1 over x, and we have different interval from 3 to 4. So firstly you have to check the conditions of the M.V.T. So in part A you have to check that f is continuous in the open interval from 3 to 4, and we have x minus 1 over x. The second term is a rational function, so the domain of our function f is x greater than 0. So in our interval all the values from 3 to 4 are greater than 0, so we can conclude that f is continuous in the open interval, closed interval, sorry, from 3 to 4. For the second condition, you have to find f prime to check if the function differentiable on the open interval or not. So you have to find f prime of x, and f prime of x equals to 1 plus 1 over x squared. And f prime is defined when x not equal to 0, not equal to 0. So we have in our interval we don't have any 0 because we are talking from 3 to 4, so there is no zeros in the interval. So f prime is defined in our interval, and hence f is differentiable on the open interval from 3 to 4. Now what's the conclusion? The conclusion, there exists C in the open interval from A to B such that f prime of C equals, this is A and this is B. So we have f of B minus f of A divided by B minus A, 4 minus 3. Now f of 4 equals to 4 minus 1 over 4 minus f of 3 equals 3 minus 1 over 3 divided by 4 minus 3, which is 1. So no need to write it in denominator, and you will get that f prime of C equals 4 minus 1 over 4 equals to 15 over 4 minus 3 minus 1 over 3 equals to 8 over 3, and by rationalize the denominator you will get 13 over 12. So we have f prime of C equals 13 over 12. Now f prime of C given here, this is f prime of C, so we have 1 plus 1 over C squared, this is f prime of C, equals to 13 over 12. Add 1 to both sides, you will get 1 over C squared equals 13 over 12 minus 1, and this is equals to 1 over 12, and by cross multiplication you will get that C squared equals to 12. So you have to take square root for both sides, and you will get C equals to negative square root of 12 and C equals to square root of 12, and square root of 12 approximately equals to 3.4. So square root of 12 belongs to our interval from 3 to 4. So this is the first value of C. For the second one, we have C equals to negative square root of 12, which is negative 3.5. So this is out of our interval, not belongs to our interval from 3 to 4. So we have only one C, which is square root of 12. And that's it. Thank you.